Okay, so it's time. It's time. Drink of water, that'll be time. Ours is really bad. Really try. But she really okay, so let's go ahead and get started. Okay, we're starting. So as you can tell from what's up on the board, today we're going to talk about the stack. That's the one segment left of real memory that we haven't discussed yet. Right? Because remember, real memory is made out of the code segment, data segment, stack segment. We talked about code segment where the instructions are. We talked about the data segment where you would put an array of data, let's say, like you did in one of your assignments. And now we're going to talk about the stack, what it is, and the basics about it, how you would code for it, and then also how you would use it. And then after that, we're going to talk about how to do subroutines in assembly. And you'll see the stack actually comes up in one of the subroutine examples that I have. And as I mentioned last week, I'll return the midterms. I'll do that after the lecture. Well, actually, it'll be after the lecture, and also after I talk about the grading criteria and what to submit for the final projects, both the software final projects and the hardware final projects. Remember, today is the last in-person meeting. This Thursday is an open lab for you to work on, whatever you need to work on, whether it's catching up or getting ahead.
Can you show up for the whole lecture and lab period for open lab, or is it just the last hour and a half that's open?
You're not required to attend for the open lab.
But if I want to, can I go any time?
Yeah, the room will be open there. So, I mean, this room is open. I have 3 sections in a row. I have an 8 to 11, 12 to 3, 8 to 6. So this room's going to be open the whole day. So you can come in anytime. Yeah, I'm not here on Thursday, but I'm available on Zoom. Same thing. The last 2 weeks is devoted for you to work on the final project again. You don't have to attend during class time if you don't want to. And again, I'll be available on Zoom for any guidance that you need troubleshooting your final project. Do you guys have questions over there? Okay, so like I said, we get the lecture part. I'll talk about the grading criteria for the final project, and then I'll get back to midterms, and I'll make some comments about the midterms at that time before I end that. Okay, but we're gonna start here, and it would be useful to have, like a computer looking at the lab manual that has like the different segments, it has a picture of the segments, and also like the instruction manual and the Otter diagram. We're going to be referring to those things during the class. So like I said, we haven't talked about the stack segment yet. Now, what's below the stack segment? Like what segment is right here? The data segment. And below the data segment, the code segment. Where does the data segment start? At what address does the data segment begin at? Yeah, X6000, right? Because you have to use that in one of the assignments, right? You did that already. Now, I'm just going to write the last 4 text characters. Understood the first 4 is 0. Okay, I'm just going to put X6000. 14,000,000. And then what is the first address of the stack? Now that one you might have to look up. You haven't used that yet. Yep, admin 30. Yeah, I think I heard someone say, hi, that would be before the data segment, that's the last address of the code segment. But yeah, the beginning of the stack starts at F. And then 3 zeros. Okay, and then what's the last address of the stack segment? 4X. Yeah, all X. 4X. Again, there's 4 zeros before the 4X, but I'm just writing the last 4 X starts. Right, so those are our ranges. Now, the stack segment, just like the data segment, just like the code segment, all of real memory is byte addressable. So just like, we talked about the code segment and the data segment, how each row is 32 bits, and that's divided up into 4 bytes, right? Each byte has an address. Same thing with the stack. Okay, so what would the address of this byte be? It's the last byte of the stack segment. Well, this is the last address, right? So this would be all that. Well, 0, 0, 0, 0, all that. The last 4. What would the address of this byte be? Yep, FF8. And what would this one be? D, right, like that. And then what would the address of this one be? We'll see what we did. All right, but again, just like the data segment, the code segment, we're byte addressable, the stack is also byte addressable. But here's the thing, and see what you have to keep in mind here, and one of the key characteristics of the stack is that it's a simpler memory construct than what the data segment. And one of the ways that the stack is simpler is that only words are written to or read from the stack. So even though the stack is byte addressable, we only use the word address because we only write and read words to the stack. See, that's simpler than the data segment, right? Because we talked about how in the data segment you can put words, you can put bytes, you can put half words, right? In fact, when we talked about that during the lecture, I had some examples where we would have to figure out the address of where particular data was, where like a particular byte was, or a particular half word or a word. Okay, so the stack is intentionally made this way to make it simpler. It's simpler than like an array of data. Okay. All right. Now another thing is writing to the stack. I'm writing to the stack. It's called a push. Okay, so when we say we're pushing to the stack, it means we're writing to the stack. A read from the stack, you know what I mean by these little tick marks, right? Just repeat what's above. So a read from the stack is called a pop. Okay, so a pop is just your reading from the stack. Now to access the stack, we keep track of the top of the stack. And I'll explain and show what we mean by the top. And the way that we keep track of the top of the stack is with a special register, SP. Now I didn't have enough of the hard copy readouts that show like the different registers and their alternate names, different registers and their alternate names. But does anyone have it on their computer? And can you tell me what the SP stands for? Register 2. Well, it's register 2. So, yeah, and SP stands for stack point. It's one of those special registers. Right, remember how we said there's 5 special registers, right? X0 through X4. X0, the 0 register, because it always has content 0. X2 is the stack pointer. X1 is the return address register that we'll get to when we get to subroutines. And then there's 2 others. I forget, it's what, global pointer and thread something, but we're not going to use those, so you don't have to worry about them. That's X3 and X4. But you see, what the stack pointer does is it keeps track of the top of the stack with an address. Okay, so the stack pointer is always going to have an address that's the top of the stack. And that's what we mean by a point. Right? If you think of it as, you know, it's always pointing to the top of the stack because it has the address of the top of the stack at all times. Okay. Okay. So the next thing is, see, there's different types of memory constructs, and the stack in the otter is a LIFO. Okay, does anyone know what this acronym stands for? Because people have seen it in, yeah, you've seen it in previous ones, right? It's last in, first out. You might have heard of FIFO too. There's first in, first out, but this is last in, first out. Okay, and you'll see what that means as we go through some examples. So, for visualization purposes, you can think of the stack like this, where, you know, we'll put some data, a word, again, you can only store or read words from the stack. So, you know, we'll put some word in the stack, and then the next word, we think of it as being on top of what we previously had in the stack, right? And then the next word goes on top of that. So, because this is a way of visualizing it, that's where the name comes from. Okay. So, oh, the other thing is the stack is filled in this direction. Okay. You may recall that the data segment we fill in this direction. Okay, with the data segment, we start at the lowest address. With the stack, we start with the highest address. And there's a reason for this. Okay, there's a reason why we go this direction with data and this direction for the stack, and I'll get to that later. Okay, but that's just for now. So my question to you is this: what word address is the first stack data at? What was that? 0x0. Well, remember, we're storing, no, like either adding or removing from this direction. Okay, F000, that's the other end. So if we're filling the stack from this direction, what would be the first address? First word address. That's what right. That's C. Oh, I thought I was last stack. Say that again? Oh, I thought I read last stack. Well, if we were going this way, that would be true, right? If we were filling this way, then, you know, this would be the first address, but we're filling that way. Is it the last address? What's that? Is 0x000 the last address that you write stack with? Yeah, that would be the last word address. That's true. Yeah, the first one would be up.
So like if you had a full stack and you had an F, basically, you have to like pop a whole bunch of them before you get to the one at F000.
Yeah, we're gonna get to that. Yeah, you're a little bit ahead of me. Yeah, we'll get to that. So, but first, getting back to this, so it's gonna be F F C. All right, and again, the word address is kept in the stack pointer. Okay, which again is registered to X2. Now, where would the second word in the stack be at? This is at FC. Where would the second word be at? And again, we're filling in this direction. We already have a word here. Yeah, it's gonna be the next word address, which would be what? FFF8. Right, next one would be at FFF4. Okay, and so on. So let's look at this example code. Now, let me say right off the bat, it's in my previous sections, I guess, this isn't a new concept for everyone. I guess the stack is talked about somewhere else. So let me just say right off the bat that this example code, it's not the only way to do what I'm about to show you. Okay, it's probably using more instructions than what you would absolutely need. But I chose to do it this way because I just think for someone who's never heard about a stack or never seen code that relates to a stack, whether it be a higher level code or assembly language code, this explains it more clearly than if I did shortcuts. Because there's ways to do shortcuts and end up with the same thing. Okay, but I'm doing it a more, drawn out way for learning purposes. Okay, so I just wanted to put that up there. Okay, so let's look at the first instructions here. LI. You've seen an LI instruction before. What instruction is that? Load immediate. So what's it gonna do? What's this load immediate instruction gonna do? Right, it's gonna take this number, right? And it's just gonna put it into our stack pointer, which is register 2. Right? So this puts into stack pointer, which again is register 2. And really what we're doing here is we're initializing, I think there's another I here. I'm not the greatest speller, so hopefully that's close enough. We're initializing the stack pointer. And you see, we initialize it to just outside this range, right? Because 1 and then 4 zeros is 1 more than 4 zeros and then F. Okay, and you'll see why we do that in a second. So actually, we're starting the stack pointer like here. But as you've learned in this class, at least what should be apparent by this time in this class, is that you don't know what's in a register until you put something there, right? So this is just ensuring that we know what's there initially. And you'll see the reason why we put it at this particular address, coming up shortly. Okay, so that's all we're doing. We're just making sure that we know what's in the stack point, right? Because if we don't do this, there's something in that register 2, but we have no idea what it is. Okay. All right, so the next instruction is an add I, right? And you've seen this instruction before too, right? So what does this instruction do? And there's a comma here that I had left out, but
Doesn't it de-increment the stack pointer by 4?
yeah, that's what it's going to do, because what's happening here right, exactly. It's going to take the stack pointer as a source register and take its contents, which is the 1 and 4 zeros. It's going to add -4 to it, and then put the result of that subtraction right into the stack pointer. So this is going to change the stack pointer to what? Because if I take 1 and 4 zeros in X and subtract 4, what do I get? What is it going to be? Right. C, which is the first word address of the stack. Right. So you see what this instruction does is that it moves the stack pointer to the word address SFC, where we're going to put our first word in the stack, because the next instruction is a store word. And as we said, a push is the same as a write, and a write is the same as a store, right? So this here, this is a push. Okay, you do a push with the store word. So how does a store word work again? What is it?
What's the address in the register inside of,
Well, it uses the address, right? This is gonna be our address, right? Because it's gonna add the 0 to what's already in the stack pointer, which is that FFFC. It uses that as an address. It's gonna take the contents of T0 and put it at the address of the stack. Right, so you see, this is gonna take, this push is gonna take the contents of T0 and put into stack at address FFFC. So this is going to take T0 and put it right there.
Why don't you just load the immediate? Okay.
Yeah, like I said, there's other ways to do it. Like I can show you after lecture or anytime, but not right now because I want to do this again just from a learning perspective. I can show you this like this whole thing like in 4 lines. All right, so yeah, there's a much more efficient way, but again, I chose this way just I think it's when someone's first learning it, hopefully it's clearer this way, even though it's more instructions than what you absolutely need. So yeah, I'm glad you're seeing that. Hey, this looks like it's longer than what you need, and you're exactly right. Okay, but is everybody okay so far? So does everybody see we're initializing, then we're putting the stack pointer to the address that we want to store the data at, and this is what does the storing of the data. And again, we call it a push. So everybody's good? All right, well, if that made sense, the rest of it should make sense because now we're going to change this second add-I here is going to change our stack pointer to the next word address. We're going to move this up to FFF8. Right, so you see this here is stack pointer to FFF8. And now we're going to put T1 into that part of the stack. Right? And then this next add-I, right, is just going to put the stack pointer to FFF4, right? So it's going to move it up here. And then this store word is going to push T2 data into that spot of the stack, right? So again, we visualize that as we're pushing data, that data is on top of the data that we had previously pushed. Right? That's where the name comes from.
and store write as a reminder is that the same as like writing to memory? Or store word?
Yeah. Well, we were using store word for you could use store word to put data into the data segment. Now, again, a difference in why the stack is simpler is with the data segment, you could not only store word, but you could store bytes or half words. Okay, but again, the stack, we only store word. So you would only use a store word for a push. You would never use a store byte or a store half word with the stack, where you could use those for the data set. Okay. Okay. Well, like I said, this is all pushes. Right, the store words. Okay, now to pop, right, to read data from the stack, you use load word. Right, so these would be pops. And this is where last in, first out comes into play, right? It's a LIFO, so we would start with the data that was last put in. It's the first to come out. So the last to be stored is the first to be read. Okay, so you see here, this first load word, I already have FFF4 in my stack pointer. So I wouldn't add an offset to it, right? I'd make my offset 0. So it's going to take the data at this address of the stack and put it into register 2, right? So this takes stack data at FFF4 and it puts it into T2. Okay, then the add-I moves my stack pointer, right? So the stack pointer here, I'm adding 4, so it would go to FFF8. And now I'm reading the data from that part of the stack, right? So the stack data, looking up here, stack data at FFF8 gets put into P1. Right, move my stack pointer again, so I get to FFFC. So that would be here, right? Stack pointer to FFFC, and then I have another load word that's going to put the stack data at FFFC into register T0. And then I would have another add-I here just to put my stack pointer back to my initial value of 1 and 4 zeros. Okay, so this is always the situation that whatever order you pushed, right? We went T0, T1, T2 when we pushed, you do the opposite order when you pop, right? It's first T2, then T1, then T0, right? And that again goes back to because it's a last in, first out type of memory construct. Okay, so was this clear? And again, you can think of ways, I'm sure, that this could be done in less instructions, but this is the whole idea of it. Okay, now, can you see that you would always want the number of pushes to equal the number of pops? Can you see why we would want that? Because what could happen if we had more pushes than pops or more pops than pushes? Yeah. Say that again. Right. If we were pushing more onto the stack than what we were popping, we could go into the data set, right? We could start putting data intended to be on the stack into data, and that could have bad consequences because it would possibly overwrite something in the data segment that you're using that we didn't want the stack to be part of. Or the other direction, you could go up into this area, which I think is unreserved or reserved, where who knows what's there? You don't know what's there, so you could be reading data that you have no idea what it is. Okay, so you always want to neutralize your pushes and your pops. You want the same number so they cancel out. Yeah. Remember earlier I said that the data segment we typically fill this way, right? Starting at the lowest address. In the stack, we always start up at the top. Well, can you think of a reason why we would want that instead of say this? And before you answer that question, think about what we talked about before. These address ranges, right? The address range of data, the address range of stack, and also the address range of code, which you don't care. What sets those address ranges? Are those set by hardware? Yes. These address ranges are set by hardware. The address range of real memory, the entirety, like all of this, like all of the segments together, right? Real memory, all the segments. That range, that address range is set by hardware because that's set by the FPGA that's on your board, right? The basis board. But these address ranges of the segments, those are set by the programmer.
Is it because if you change it, you have to change the start point every time you change the limit, and otherwise it can just stay the same because you're changing the partition between the two?
Right. Well, yeah, you're on the right track. That the reason why we would want to do it this way, as opposed to what I had earlier, is because then this border between the stack and the data becomes flexible. Right? That if for some reason I needed a bigger data space than what I have compared to the stack, I could easily move it. See, these address ranges of the code segments, those are in the memory module of the Otter. Dr. Hummel is the person who set these address ranges. But you could go in there and you could very easily change that. But you see, if you did this, right, if the stack was like this, well, then you're artificially setting this. Right, you no longer have the flexibility. Right, you're limiting your data segment to this amount and your stack to this amount. But by doing this, the programmer can easily change how much memory is allotted to the data segment, how much is allotted to the stack. Yeah, so it's done for flexibility reasons. And again, it's because these ranges are not set by hardware. You know, the registers in the stack and the registers in the data segment and registers in the code, they're all the same registers. They're all 32-bit registers that are byte addressable. You know, they look no different. Okay, it's just the programmer that's deciding what part of the memory does what. Okay, so let's see, where are we at? I think that's all I want to say. That's all I wanted to say about the stack for this time. Now, when we get to one of my examples for subroutines, we're gonna come back and see the use of a stack. Okay, but are there any questions up to this point? Everybody's okay?
Yeah. So how do you stop it again from like going into the data segment? Like
This.
wait, so what if you do have the number of pushes equal to the number of pops, but what if you still push too many times into the data? Wouldn't that still go over?
But pops cancel out pushes, right? Because as I'm pushing, right, I'm going this way. As I'm popping, I'm going that way. So as long as my pushes and my pop equal, I end up back at the same place. It's only when they're unequal that I could possibly, like if I have more pushes than pops, I could possibly go into the data. If I have more pops than pushes, I could possibly, you know, be up here somewhere. It's like I said, it's reserved or unreserved or reserved thing, sorry. Yeah. But if they equal, they effectively cancel out because the stack pointer will end up at the same place if they're equal. Okay.
But even if you like, I'm saying if you push it like I don't know how many different words you can put in the stack, but like what if you push more words than that? And even if you pop it, aren't you still pushing to the data? Won't that still cause a problem?
Are you just saying like you just do as many pushes until you get here before you pop the first time?
Yeah.
Okay, well, yeah, clearly that's a problem. You wouldn't want to do that. There's, you know, again, you could possibly move this limit because again, it's easy to do. But yeah, if you didn't move this limit and you just did a bunch of pushes with no pops and you know, you didn't do pop it until you were in here. Well, yeah, you've also overflowed. That's called a stack overflow.
So that's up to us.
Yeah. The hardware is not going to have like a, you know, a flag or something that says, hey, you violated it. You know, you violated the address range of stack. Yeah. So yeah, you got to be aware of it. Yeah. Okay. Any other questions up to this point? Okay. All right. Let's talk a little bit about the basics of a subroutine, and then we'll take a short break for like 5 minutes, and then we'll talk about the code I have up here for subroutines. Okay, the first thing, subroutines are useful when you have repetition in your program, like you're doing the same thing over and over again. You know, some examples like multiply, you know, or divide, or sorting. Also delay. In fact, that's something you might need for your final project, right? You might have to put a delay so it gives the enough time to change switches or the output enough time to change so you can see like successive output data. And I'm sure you can think of others, right? But you know, without knowing a subroutine, if you had to do something like a multiply like 20 different times, you know, you would have to basically do like a copy and paste in your program in RARs, right? So subroutines are especially suited for, you know, operations or functions that you're going to do multiple times. And in fact, you know, in some languages, some computer languages, subroutines are called functions. Okay, in fact, in Arduino, some of you have used Arduino, you know, like use functions in Arduino. Well, it's just a subroutine. Okay. Now, the reasons for subroutines is that it provides a way of modularization. Very hard word to use. It's easier to explain than so. What we mean by modularization is that, we're taking a big problem and splitting it into smaller problems, right? So we take a big problem, split into smaller problems. We have smaller, we have split into smaller problems. Right, so you have some big complicated program that you have to write. And you can take that big complicated program that's going to solve some, big problem. And you can use subroutines to solve it, where the subroutine is solving like a part of that big problem. Okay. Also, subroutines make your code more readable. My spelling's not the greatest. I think that's readable. Right, just from, and you'll see when we get to the flow charts, just by having subroutines that are, named in a descriptive way, it's easier to look at somebody's flow chart to that program and say, oh, this particular thing's happening here, this other part of the problem is being solved here, and so on. So it just makes it more readable. Also, through the use of using our registers and the alternative names that we have for the registers, it makes our code more reusable. Okay, this gets to what we're going to talk about next, where some of the registers that we have are, the A registers, which have a specific purpose, T registers, and S registers. So if you were to look at the page, and again, I didn't have enough for every table. I put some on some of the tables, but if you don't have a hard copy of on the table, you should be able to see it on the computer. But it's that page that shows the alternative names for the registers in the reg file. We've got like T0 through T6, and A0 through A7, and S0 through S11. And we're going to see, what we use these for. But first thing, parameters, what we call parameters in subroutines, those are the values that get operated on. So and these are the values that are passed to the subroutine or given to the subroutine. So an example of a parameter, if you have a subroutine that's going to multiply two numbers, the two numbers to be multiplied, those would be parameters. And the way the main program would pass those values that are going to be multiplied, those parameters, to the subroutine is just by putting them in registers. Okay, because that's another thing that should be apparent at this time in this course, right? That in order for any data to be operated on, right, to do any sort of operation like an AND operation or subtract, whatever it may be, that data's got to be in a register, right? Because the operations occur on the contents of the reg file registers, right? Like your RS1 and your RS2. Okay, so that's what parameters are. Those are just the values that we're operating on. And then return value, that's the results. Okay, so after you multiply two numbers together, let's say, the result would be your return value. Now, how this works into our, names of our reg file registers is that registers A0 through A7, those are for parameters. Okay, so you would only use those registers for, the values that are going to be operated on. Registers A0 and A1, those are for the results. Now, a lot of times your subroutine is just going to have one return value, one result. Like say when you multiply, the result of that multiplication, that would be your result. So you would use A0 for that result of the multiplication. But you could have a subroutine like division where you want to keep not only the quotient, but you want to keep the remainder, right? So that would be two results. And for two results, you would use A0 and A1. Okay, then we have the temporary registers, right? T0 through T6. And ideally, subroutines only change temporary registers. Okay, so ideally, subroutines only change the temporary. Okay, I'll abbreviate with temps. And ideally, subroutines do not change the save registers. Okay, and did I get this right? Is the highest save register S11? Yeah, okay. Yeah, that was from memory. Usually when I try to use my memory, I mess something up. But. So you can see there's 12 registers for save data, there's 7 registers for temporary, and then you get the 8 registers for the parameters, of which out of those, you use a couple of them for results.
When you say ideally, do you mean like you have like a really big function where you just have to use S0 and S1? I don't think it's okay to use them, but just try to use the other ones first.
Yeah, we're gonna come back to this because it also involves the stack. Okay, so yeah, I'm gonna come back to this, but yeah, I put ideally because like you said, you could have like a large program where you just run out of temporaries. But you're gonna see that's where the stack can be helpful. Okay, any other questions before we just go over these 2 flowcharts? And like I said, we'll take a short little break before we talk about this code. Okay, here's an example involving a subroutine because up until this point, you haven't used the subroutine, but you've done flowcharts, right? Each software assignment had a flowchart. So you should be familiar with all these symbols in the flowchart except for this one. So this is the one for a subroutine. You can see it's just a rectangle with like 2 bars on the end. And you would put the subroutine name in the middle here. Now, another difference is when you have a subroutine, instead of having this oval with start like you've been doing, you would either put main like I've done here, or you could put the name of the main file. Okay, so don't put start here when you do a flowchart that involves a subroutine, either main or the name of the main program. It still would end, okay, like you've seen in previous flowcharts, but when you have a subroutine, the subroutine is going to have its own flowchart, right? So your main has a flowchart that shows when the subroutine occurs in that process of the main, and then you show the flowchart for the subroutine, and you start it with the subroutine name, and then instead of using end, you use return. Okay, and you'll see why. You'll see what return means when we do these couple of examples. Okay, and I'm also going to turn the camera. I haven't forgotten today, and I think the reason I haven't forgotten is because I've taken a break at this point, so it gives me time to actually read what I wrote. So yeah, let's take a short break just to the top of the hour, so about 5 minutes or so, and then when you come back, we'll go over these 2 examples. Then, like I said, I'll go over the grading criteria for the final projects, and then I'll hand back your midterms. And then after that, you have time to work on your assignments if you want here or someplace else if you don't want to stay here. So we'll start again in about 5 minutes.
I also think that one of my having red file
Okay, so let's go ahead and start again. I think it looks like everyone's back, or most people anyway. Okay, so there's just 2 examples I want to go over that involve a subroutine. One's a very basic example where the main program is calling a subroutine. That's how we go from the main to a subroutine. It's with a call instruction. And then the second example is a little bit more complicated because it involves a subroutine calling another subroutine. Okay, and you'll see that a problem arises in this case that you can solve with using the stack. But let's start with this one here. So in this example, I put .text this assembler directive just to, what's that? Camera. Oh, I didn't turn it. I thought I turned it. I didn't turn it. Now, after I said I had, geez, I jinxed myself. Thank you. You noticed that from back there that I hadn't turned it. That's very good. I appreciate that. Thank you. I tell you. Thanks.
Thank you very much. I didn't get the text sort of there.
All right, well, thank you. All right, but anyway, getting back to it. So, I put this assembler directive, right, the dot text here, even though it's not really needed because I don't have like any data segment up here or anything, but I just put it there just to remind you about assembler directives and, you know, if you don't have like, say, a data segment before this, right, it's gonna default to this, right? So we don't absolutely need that, but I just put it there. But anyway, here's our main program, and within the main program, we're gonna use a subroutine. So you use a subroutine, you use a call instruction. Okay, so if you look in your instruction manual, you'll see call, and then this is the label. And then you pick a label where the subroutine starts. Now, I intentionally left out something here. What did I leave out here between where the main program ends and the subroutine starts? Because you've seen this before, I mean, not with the subroutine, but you've seen where, like in a program, once it's done with a certain instruction, you don't want it to go into like the next. Yeah, you just use what we call a trap. Remember where you have a jump that just jumps to itself? Right, it's called a trap. Right, because we don't want to go into our subroutine after the main is done, right? We just want to go into the subroutine when it's called by the main program. Okay, so this trap will stop after the main is done, going into your subroutine when you don't want to, right? Okay, but getting back to this, this call instruction, if you look at your instruction manual, that call instruction, it's a pseudo instruction for a JAL. And we talked about the JAL instruction. Right, specifically, what's the L stand for? Link. And then what's a link?
Store the address.
What address?
The address is jumping through, like the next address.
Yeah, the next address, right? See, the L is a link. And if you go back and you look at the data segment or the data path diagram that we did for JAL, well, in the data path of a JAL, we use this connection that's right on the other side of the +4 block where we've added 4 to the current program count. And you see how that goes up to the mux that's above the reg file? Because we're taking that PC +4 address and we're storing in a register because we're going to need that in order to return back. Okay, so you see this call instruction, which again is a pseudo instruction for JAL, it's going to save PC +4. And that's the address of this instruction that's after the call, right? Because once we're done with the subroutine, we want to return back to that instruction. So the address of that instruction, the PC +4, it's going to be saved. And it's saved into the RA register. Okay, you know, that's one of the specialty registers. What does RA stand for? Return address. And what register is it? Register 1. It's X1, yeah, register 1. Okay, so you see, we want to save the address of that next instruction after the call because we want to return to this once the subroutine is done. Okay, so, you know, it's going to call the subroutine. So now the program's going to jump down to the subroutine. It's going to do whatever the subroutine does, right? And then it hits this return. And when it hits that return, it then goes back to that instruction immediately following the call instruction. And you see a return, if you look at the instruction manual, the return is a pseudo instruction for a JALR. Right, the R involves a register that, you know, we're adding to the current contents of the return address register, which we make 0 here because we want that return address. And then it also has an L, so it also has a link. So this return instruction is also saving the PC +4, but look where it's saving it. It's saving it to register X0. And what do we know about register X0? Right, there's always zeros there. So do you know the reason why we're putting that PC plus 4 into X0? Because it's just gonna essentially get rid of it, right? And why? Why is that okay to just get rid of it?
Because after we return, we don't need to go back to it.
Right. You're never gonna go back to this instruction, there is no instruction here, right? You're never gonna go to this address. And the reason you want to put that link address into register 0 as opposed to some other register is you don't want to possibly overwrite data that you care about in some other register, right? By writing to 0, it's just gonna make whatever you try to write there 0. So you don't overwrite anything.
I'm looking at the manual call, and it says, I get why you add PC plus 4, but the call says it's adding PC plus 8. I don't get why I would add 8. Four makes more sense.
I don't, where are you reading this?
In the manual on page 25. The call,
Let's see, plus 8. Where do you see plus 8?
it's like the RTL.
Oh, that's gotta be a typo. Yeah,
Well, no, I don't think it is, because when you look at like the usage, it says the PC is like 10 and 14.94, but when you save it, 91, it's 14.98 seconds.
oh, you're looking at the thing below?
Yeah, that too.
Yeah, I mean, I don't have an answer for you. I mean, I've never noticed it, but it's saving PC plus 4 because we want the instruction after the call. So why it says plus 8, I don't know, but I can check. But I'm thinking it's a mistake. Yeah, because plus 8 would, it'd be this instruction here, so you'd be skipping over whatever this is. That doesn't make sense, right? Because you want it to be the next instruction after the call, not 2 instructions. But I will check to make sure, but I'm like 99.5% sure.
All is a pseudo instruction. No, wait, all you can see is dollar package of what those two instructions. So you need 2 to jump over. You need to add 8 to get over.
Well, this pseudo instruction, like right here could be 2 instructions.
Yeah.
But still, this is after those 2 instructions.
No, it does it so that it does how PC so that when it does do it, it jumps over the job, I think.
Oh, so you're saying like, oh, I see what you're saying. You're saying like this call is 2 real instructions.
Yeah.
And it's essentially going from this one to this one, like it's jumping over this. All right, that could be true. The only reason why I'm still not convinced is because I took this right out of Dr. Hummel. I mean, he does the same example and he explains it the same way. So I'll have to check with him. I mean, this is almost verbatim how he teaches it. So I'll have to check either this is a typo or he wasn't aware of this either. But I will check with him. All right, but the key point is whether it's plus 4, plus 8, the key thing is you want to go to the instruction right here.
Yeah.
Okay, so we agree there, and I'll have to see what the discrepancy is. Okay, any other questions up to this point? All right, so let's look at this example. This is a subroutine calling another subroutine. So, same thing as we talked about before. Here's our main program. So the first call is to this subroutine 1. So just like we said before, it's going to save this address, whether it's PC plus 4 or PC plus 8. I'm still going to put PC plus 4, but again, that's something we have to iron out. And it's going to put that address into the return address register, right? It's going to say that return address PC plus 4 into RA, which again is your register 1. Okay. All right. So again, I left out the trap here just like I did before. So again, you would need a trap here, right? Just so your main doesn't go into your subroutine inadvertently. Okay. But now, as you can see, inside our sub 1, we have a call to subroutine 2. So again, at this call, it's going to save it's gonna say the address of this instruction right after that call. Okay, so now it goes into subroutine 2, it does whatever instructions are here, and then it hits this return. So where's it gonna go now when it hits this return? Because what do we have in the return address at this point?
The parameter.
What parameter?
Oh, never mind.
Like what got stored in the return address register before this return?
The address of also.
Right, see right here, this address and this instruction right after the call sub 2, that's what's in our RA. So that's when we hit the return, that's where it's gonna go. It's gonna go to whatever address is in this return address register. So it's gonna go right here to this instruction. And now it's gonna process these instructions and it's gonna hit this return. And where's it gonna go when it hits this return? Because what's in the RA register at this point? Has our RA register changed between when we returned here and we did all this here? No, it's still the address of this instruction. So you see, that's the problem here. Is we could just get stuck. Right? We wouldn't go back to the main program. And that's because this return address register, you know, this return address for the main got overwritten here. Right? So even though it was okay for this return, well, now we're just stuck here because we're at the return address, you know, of this instruction. Right? So does everybody see what the problem is? The problem is that this return address for the main got overwritten. Right? And that's what keeps us in this first subroutine, right? We can't get out of it. Well, the stack can solve the problem. Right? Because what I can do to solve this is I can use the stack. That right here, the first instruction of this subroutine 1, I push RA to the stack. So I'm going to take this return address for the main and put it on the stack. And then I would pop it right before this return, right? Because if I pop it right before that return, it's going to put this return address of the main into RA before I hit this return, and that's going to take me back to the main. Oops. Yeah, this instruction again. Okay. So you see, that's one use of the stack, is that if you have a situation like this where you need to temporarily put data someplace so it doesn't get overwritten, the stack is very useful for that. Also, another use of the stack is what Grady was referring to a little earlier, is that, you know, you could essentially use the stack for temporary data. Like if you run out of temporaries for your subroutine, you could start putting temporary data to the stack temporarily. And again, just pop it off when you're done with that subroutine. Okay, so those are the primary uses of the stack. It's usually something involved with when you're using subroutines. Okay, so any more questions about anything we talked about up to this point?
Oh, I just want to mention, I think for the call, I think it's supposed to be program counter plus 8 because it's a pseudo instruction that uses 2 other instructions.
Yeah, that's what Landon was saying, and I will check on that. Like I said, I understand what you're both saying. I just need to check because, like I said, I took this right out of Dr. Hummel's lecture. It's the same examples he uses in his lectures. So yeah, let me talk to him and see if it was just a mistake or if there's something else. But yeah, I will check on it because I'm not sure at this point. But what I am sure, you know, I'm not sure whether this is PC +4 or PC +8. But what I am sure is when you return, you're going to the address of the instruction after the call. It's not like 2 instructions after, it's this one. And yeah, this may be the 2 real instructions that you're talking about, but you're jumping over the second reel of the call. Okay, that could be, but like I said, I'm not 100% sure. Okay. Okay, any other questions? Okay, so The next thing is I want to show you the grading criteria for the final projects, both the software and the hardware. And like I said, once we're done with this, I'll hand back your midterm. But I just want to make sure this is clear. It's on Canvas, but just want to go over it clear. Okay, so like I said, this is right off Canvas. First thing, and I think I've mentioned this, but let me say it again, that unless you tell me, I'm just gonna assume that you're using the same software partners for this final project software. Okay, so I'm just gonna assume it's the same two people as it has been for the software assignments earlier in the quarter, unless you tell me different. And if it's gonna be different, tell me by the end of this week. Just send me an email and tell me, you know, what the group is. Again, it's a two-person group for the final project software. And as you can see here, what you're asked to do is to write an assembly language program that chooses between two subroutines. And it's determined by the value at this address of real memory. If the value at that address is a 1, it's going to run subroutine number 1 or subroutine, or it's going to, the subroutine is going to run software number 4 part 1. Okay, and if the value at that address is something other than 1, the subroutine is going to run software number 4 part 2. Okay, so software number 4, that was a software assignment that we skipped over. Okay, and the reason we skipped over is because it wasn't introducing anything new at that point. It was just another problem involving concepts you had learned before that. And I decided to use that as a final project and also modify it by using subroutines for each of the parts. Also, I've added that for parts 1 and 2. Now, this may not apply to both parts, but whatever part it does apply to, make sure to show a result of 0. You know, if the result is 0, that should be displayed, because it doesn't specifically say that in either of the parts. And then also, if you have a case where you're dividing by 0, indicate that that's an error. Okay, and it's up to you how you display that it's an error, but you need to show if you're dividing by 0 that's some error. Okay. Now, as far as what you submit, is there somebody out there? As far as what you submit, it's the same as what you've been submitting for previous software assignments, with the addition that because you're using subroutines, you're going to have more flowcharts, right? Because the previous software assignments didn't have subroutines, so you just needed one flowchart. But here you need a flowchart for the main, and you need flowcharts for each of the subroutines. So it'll be 3 flowcharts. And each person, right, because you got a 2-person team and there's 2 subroutines, each person has to take responsibility for a subroutine. Okay, and you know, at the top, you know, in the comments of the subroutine, you know, write the person's name that's responsible for that subroutine. Okay. Let's see. I don't think there's anything else. Did I talk about everything that's up here? I think I did. All right. So, do you have any questions about, you know, what you need to do and how it's graded? Right. It's the same grading criteria, like I said, as the previous software assignments.
So isn't it there also programs that in the subroutine, like who should be responsible for like the thing that chooses the subroutine?
Yeah, you'll see in this particular case, the main should be very little, because you just need something to choose between, you know, whatever the value is. So yeah, I'm not so concerned about who puts their name on the main. I put both people's names. But yeah, each subroutine, I need to know the person that's responsible. You know, the reason I say responsible is that I'm sure both people are going to be working together, but you know, one person has to say, hey, I'm responsible for this part. Okay, if you put both names, you know, if you don't follow directions, and I see that, you know, a group puts both names for both parts, you're going to lose points. Okay, somebody's got to take responsibility for each of the subroutines. Okay. Yeah, remember, following instructions is important. At least I think they're important. Okay, so, any other questions on this?
Is part 1 and 2.
Well, software assignment number 4, if you look at it, it's got 2 parts to it. I forget what each part is, but one of them has something to do with division because there's a possibility you could divide by 0. Did you have a question?
Yeah, so you don't need to focus on the basis board, right? It's just
Correct.
all-
Right, yeah, this is just like the other software assignments that you've done. Yeah. What you're thinking about is part of the hardware's final project. That's where you gotta program the otter, so that you would put on the basis board, and we'll get to that next. But before we get to that, any more questions about the software final project?
Where we can't find software 4 on campus.
It should be there. Yeah, I think doesn't it say like software for modified?
It doesn't say what software 4 part of the action is.
Do you have it? I know it's there. It was. Oh, it's under meetings, what did you say, meeting 15? Yeah, it's under meeting 15 through 16. You click on it for a minute.
No, it just said work on final projects.
Wait, well, that's what I have.
The software for, this software itself, not the game. So it's under exactly.
Yeah, but under software 4, it just said exactly what you have to put up there.
It doesn't say what part 1 and 2 are.
Okay, well, let me go over the next thing and I'll find it and I'll let you know. It was there at one point, maybe something happened, it's not there, but I will make it there. Okay, but let me go to the next thing. Okay, so this is the final project hardware. So this is where you can have up to 4 people in a group, right? Because the hardware is 6 and all the previous hardware assignments, it's been 2-person groups. But for the final project hardware, that can be 4 people. Up to 4 people. So it could be still 2 if you want to stay in the same 2-person group, that's fine. It can be 3, it can be 4, but can't be 5 people or more than 5. It could be a single person, but I don't recommend that. But again, if you're gonna change the group, you gotta tell me. Otherwise, I'm just gonna assume it's the same 2 people. And again, tell me by the end of this week or sooner. Okay, the sooner the better. Okay, so far, I think I've only heard from 3 groups. There's, I think, a group in my 8 to 11, a group in my 12 to 3, and maybe somebody in here sent me something. But most groups I haven't heard from yet. Okay, so the final project hardware, you're to make a video, and there's 3 things to show in the video. Okay, one thing to show in the video is that your Otter CPU runs the all test mem file in the Vivado simulator. And in my video, right, remember last time I talked about I have a video under meeting 12 that shows you exactly, what to look for to make sure that your Otter is running, all the instructions which are in that all test mem file, and I show you what to look for in the simulator. Okay, so if you don't know what you should show, you just got to watch my video because you need to show what I show in that video. Okay, and then the other thing in the video is to put that when you put your Otter on the basis board, right, through the Otter wrapper and also the constraints file, that it works on the basis board. And again, in my video, I show you exactly what it should look like. And then the third thing is that, once you have the Otter working, you need to program it to do something. So you need to program it to do one of the assignments that you've done this quarter previously, or you could use an example that I did in class. Okay, now you're probably, in fact, more than probably, you're going to have to modify it in some way because, if you're using switches to input data, you're gonna have to put in some sort of delay to give time for the user to, change the switches. Or it could be either or both. You may need a delay on the output side too, because let's say you're outputting data in sequence, to like the 7-segment display, you would need time in between in order for the display to update. Okay, but that's where you would have to make a mem file, in RARs, and then put it into Vivado and have your Otter run that mem file. Okay, so it's one video, but there's 3 different things to show in that one video. And try to keep the length of the video 3 to 5 minutes. I mean, if you go like a minute over something, that's not a big deal, but when you start to go several minutes over, that starts to be too long. And each group member does have to be seen in the video at least for a split second. Okay, just their faces have to be seen, just so I know who is involved in the group. Okay, so that's the video, and then there's also material to submit. Submit a hard copy of your assembly language program fully commented. This is usually where people lose points, is they either don't comment their code or they very sparsely comment it. Make sure it's commented in a way such that I can look at it and very easily see what you're doing. It should also be commented commented in a fashion where if you go back and look at it a year from now, you know what you were doing. You have a question?
Which program is that?
This is the program you use to program the Otter. Like it could be one of my examples. It could be one of the previous assignments you did, software assignment. What's that?
Just proving that.
Great. Yeah, just showing that, you made this Otter thing, you spent all this time. Well, now program it to do something. And I'm just asking that you use something you already have done, so it's not like extra work, right? Because you're already doing a final project in the software that is new work, right? So this is just something you've done. Now, again, you'll have to most likely add a delay, like we said earlier, but the majority of it should already be done because you did it already, or I did it on the board. So, okay. Okay, so a hard copy of that, and then also a zip file of either your system Verilog or Verilog files, depending on whether you use system Verilog or Verilog. Again, fully commented. Now this is very important because this is where you can lose a lot of points. And you may not think it's important, but I think it's important that each file, it has to show the date and the creation time, and there's got to be a name. A student in your group has to take responsibility, or in this case, it can be more than one student. Okay, it doesn't have to be just one student in this case. Now, for the software, like we talked about earlier, that has to be one student for each subroutine. But here at the top, the title, it shows the date and the creation, unless you delete it, right? And don't delete it, because I need to see that, along, like I said, with the name or names. And then there's also a peer evaluation to submit, and I'll show you that form after we're done with this. Okay. All right. So any questions up to this point before I go to the grade criteria? All right. So the grading criteria. Okay, it works in tiers. Okay, where the best, the top tier, the best is that you have the Otter working, like it shows that it works in the sim. That shows that your Otter CPU works. It shows, or you've shown that the Otter works on the basis board, right? That shows that you connected the Otter wrapper correctly, and you also did the constraints file, which we give you correctly, okay? And also you show that you successfully programmed it to do what you want it to do, okay? So those 3 things, if all those 3 things are checked off, then you can earn up to an A. Your group can earn up to an A. The reason why I say up to an A is because you could have all those things, but then if you submit your code and it's not commented, or you get an evaluation that's a poor evaluation, that can lower it to something less than an A. Okay. The next tier is you show that the Otter CPU works on the Vivado simulator. You show that the Otter CPU works on the basis board, but for some reason you can't program it. Okay, or you can program it, but it doesn't work entirely the way it should. Okay, so something like that, it would be a grade up to a B. Also, you would have to provide a chronological list of the troubleshooting steps you took to try to fix it. Okay. The next tier would be that your Otter CPU works on the Vivado simulator, but it doesn't work on the board. Okay, and if it doesn't work on the board, you can't program it. So that could earn up to a C, as long as, again, you provide a chronological list of the troubleshooting that you did. Okay, and then the next tier is that, it doesn't work in the simulator. If it doesn't work in the simulator, it's not going to work on the board. Again, if it doesn't work on the board, you can't program it. But you could still earn up to a D grade if you do a chronological list that, again, shows me what your troubleshooting steps were. And then the last tier, which is a failure, is, it doesn't work on the board, doesn't work in the simulator, therefore you can't program it, and you don't provide what you did to troubleshoot it. Okay, that would be a failing score on the final project hardware. Okay, so does everybody understand how this goes? And you understand what I mean by up to a certain grade, right? Because you could be in one of these tiers, and if you leave something out that you're supposed to submit, or you don't do this chronological list of troubleshooting, that can lower it. Okay, so any questions on the grading criteria? I already have one group in my 8 to 11 that is almost done. They got theirs to work and they got it to program already. Yeah, I know, crazy. I guess they spent all weekend working on it. It's like 4 CPEs. They sit on that table. Maybe that table's like a magic table or something, and it has good luck. So, yeah, I don't expect that. Again, the reason why I'm giving so much time to work on it in, groups up to 4 people, because it's not easy to do. Okay, it's not easy. Also, let me just say again, I'm here on Zoom. It's just phone. Hello. Okay, but like I've said before, I'm available on Zoom during the last 2 weeks when you're working on your project. But again, I'm there for guidance. So, if you need guidance, you're having some issue, some problem that you're having a hard time with, I'll be there to guide you and say, well, did you check this? Okay, this output is okay, but did you check this input? Usually when people have difficulty troubleshooting, they'll see where the error is, but then they just focus on that module where the error first showed up, where really the problem is 2 modules away, because what's feeding into that module. So, and that's what Dr. Hummel talks about in his troubleshooting video. He shows you how you basically have to trace the signal backwards sometimes in order to get where the problem is. The problem isn't always where the issue first arises. Okay, that's usually the most common thing where people sometimes go the wrong direction. Okay. All right. So, any questions before I hand back the midterms? And I will look at where that software for parts 1 and 2 is. Once I'm done with the midterms, I'll sit down and look, and hopefully I'll find it. Let's turn this off here. Yeah. Okay, so as I have up here, and again, this is just mostly a reminder. When you get your midterm back, if you see a green circle, that means that was correct, right? That's +1. If you see an NR, that means no response. That was something that was left blank. Again, it's either a plus or a minus, right? It's 0. And then if there was an incorrect response, if it was multiple choice, I put an X with an I for incorrect. And remember, it's -0.5 for an incorrect multiple choice, and -1 for an incorrect true false. Question number 16, I threw out. And that's because most people missed it. And when I looked at it, I just realized it wasn't a good question. It wasn't really testing what I wanted. It was just an error on my part. So anyway, I threw out number 16. Now, also, when you get the test on the front page over on the left side, you'll see a number with a box around it. That's how many points. Okay, so that's, I tallied this all up. Okay, and that's how many points. And then what I did is I took that number, that was average for the class, like I figured out what the average number of points was for the class. And then I called that a 7.5 out of 10. Okay, so your score out of 10 is within a circle, like a green circle like this. And that's what I put into my spreadsheet. So the score that matters, it's not so much this one, it's the one that's circled. That's what I put in my spreadsheet. Okay, so, if you had an average number of points, it was a 7.5, if it was more than the average number of points, it was of course above that. And if it was below, it's a number below. There was one or two individuals in this section that when I figured this, out of 10, it came out more than 10. If it came out more than 10, I still put a 10, but I put a plus next to it. So in my spreadsheet, I put a 10, but then I made a note, just noting that, you actually did better than that. It's like an 80 plus. Okay. Let's see, what else am I gonna say? Oh, two more things. If you have any questions, so, if you think I made a mistake or you have a question about a question, send me an email. Okay. I scan the test, anytime I give a test, I always scan it before I hand it back. And then once I handed the test back, I only look at the scan for any questions or concerns or whatever it may be. So, if you come up and ask me a question, I'm gonna say, send an email. Okay, because if you tell me something verbally, I'm likely to forget it anyway. So having an email kind of, puts it in stone where kind of official. Okay. And then the other thing is, if you didn't do well on this test, don't panic. One thing is, if you look at the syllabus, the midterm is 10% of the total grade of the course. Okay, I made it a lot less than other classes I get midterms. Like in my CP 132, the midterms were like 30%, something like that. So it's a bigger deal. The other thing is, we still have a final exam online. That's 10%. We still have the final project. I think they're each 12%. So there's still like a third of the course grade that hasn't been determined yet. So if you didn't do well on this test, there's still plenty of opportunity to improve. Okay, so again, I wouldn't panic if you didn't do well. All right, so I think I know everybody here, so if I give you the wrong test, let me know, but I'm pretty sure I know everybody.
Okay. I was expecting
It's true. I mean, it really makes sense without finding.
Oh, thank you, sorry. Yeah.
you can't do that.
Right.